we should know hierarchy. See, we don't have any freedom on the developing the control hierarchy, right? This hierarchy they will see we can develop based on the actual system character. Whenever you want to develop the hierarchy, right? See, this hierarchy they have decided based on the actual system characteristics. See how many controllers are there here. You forget about what is there inside, whether it is a PA controller or model predictive based controller, right, or hysteresis controller, or see, you forget about type of controller. If you take any type of controller, see, this is the hierarchy. The object of torque controller is it will rectify the torque error. The object of speed controller is it will rectify the speed error. The object of position controller is it will rectify the position error. You got my point? Now you got answer. What is the problem with conventional controllers, PA controllers or hysteresis controller? What is the issue with? Before break I asked, right? What is the issue with conventional controller? What is the input to the controller? What is the input to the controller? Any controller, hysteresis, or even if you take model predictive controller, what we are doing, we are calculating error. Error is the input to the controller. You got my point? What is the output of the controller? How to decide what is the output of the controller? Controller output is always cost component. Please try to understand. See, if error is the current, if there is any current error you are giving to the controller, you don't have any option. Your controller will produce the voltage. How much voltage you need to maintain across motor terminal, your controller will decide. If you maintain same voltage across the system, right, in coming samples, coming time, what will happen? Your current error will coming down. You got my point? See, current is the effect. Voltage is the main cost component. Controller input is always effect signal. You got my point? So this effect, how we can minimize? Through cost component, through voltage. Voltage is the main cost component to control the current in electrical circuit. You got my point? Now take example, mechanical system, everyone can understand. Computer science or electronics scholars also they can understand. Now in case of mechanical system, please tell me how we can eliminate the position error. How we can eliminate the position? If there is position error, how we can minimize? Through speed. You got my point? So if you take position controller, your position controller will decide how much speed we need to maintain. The position controller output is, what is the output? Speed reference. How much speed you need to maintain in actual system, your position control will decide. Speed is the main cost component to change the position. Now take speed controller. What is input to the speed controller? Speed error, right? So if you take speed error to the controller, what is the output? Speed, how we can minimize? Speed, how we can control? Through torque. So output of the speed controller is torque or current. You got my point? Understood? So if you understand this, see what I'm trying to say is, if you take any controller, many scholars or even students after completion of control system subject, they are unable to tell what is the output of the controller. Output of the controller is cost component. Input is effect. Our aim is minimizing the effect. You got my point? Control engineers aim is minimizing the effect. If error and feedback both are not matching, how we can minimize the effect? You need to send error through the controller. Once you send the current error to the controller, your controller will produce the cost component. That is the beauty of controller. Controller will decide how much magnitude or how much frequency, how much RMS value we need to maintain across the machine. It will decide. Clear? Can I ask one question, standard question? It is not related to our system. You know about RMS? You heard about RMS and average? What is the significance of RMS and average value? What is RMS? RMS, root mean square. Our systems, all systems, whatever electrical systems are there, all are responding only for RMS value. It is not responding, our systems are not responding for instantaneous value. You got my point? What is the nature of instantaneous signal to the system? It is alternating. At every instant, what is happening? Your voltage is changing its magnitude. Magnitude is fluctuating. Even though magnitude is fluctuating, glowing is not changing. It is constant, right? You got my point? All systems are responding for effective value. Practically, all are responding. It will not respond for instantaneous value. It will respond for only effective value. How much effective time you are spending on particular problem, it will decide the output performance. You got my point? In case of electric drive also, how much torque you are producing, right? Effective torque is so important to rectify the speed error, right? So see, based on the speed, if speed error is coming down, coming instant, position error we can eliminate, right? Best example, any white paper is there so that I can explain effectively, right? Significance of hierarchy. Any white paper, A4 paper is there? A4 paper. Anyone having A4 paper? This is the standard procedure. See, in today's session, what I am focusing is, I am focusing on philosophy. If you understand this philosophy behind the mechanism, it is not a big deal to adopt same technique to your system. Any white paper is there? No problem. I will return back. I will not keep with me. I will return immediately after. See, my objective is I want to roll the paper. Let us that initially this is the position of the paper. Let us assume that. See, this is the initial position of the paper. Now how many loops are there? 1, 2, 3 loops are there. You got my point? Now if you want to roll the paper effectively, you have to concentrate on inner loop or outer loop. See, using this outer loop, we cannot roll the paper. You got my point? See, you have to take inner loop and you have to control the inner loop. What will happen if you are able to control the inner loop effectively? Automatically, outer loop will follow the inner loop. You no need to put any effects on the outer loop. You got my point? This is what we are following in any control mechanism. Here, see, torque is inner loop. Torque is there in the inner loop. After that, speed controller is there. After that, position controller is there. Finally, there are 3 loops are there. These 3 controllers are connecting in cascading fashion. Right? Your job as a designer, your focus is on inner loop. You have to decide the bandwidth of the inner loop first. Once you decide the bandwidth of the inner loop, automatically other loop bandwidth we can decide simply by using thumb rule. Suppose inner loop bandwidth is 100 Hz, right? Torque loop bandwidth is 100 Hz. Next, speed bandwidth you can take 100 by 5 times less, right? Next, position controller bandwidth you can take 100 by 5 by 5 again, or 2 you can take. So bandwidth of the inner loop should be very, very high. If inner loop is working fine, if students are working fine, burden on the teacher will coming down. If burden on the teacher is coming down, definitely burden on the HODs, burden on the deans will coming down, right? So here your job is, you need to concentrate on inner loop. You have to decide the bandwidth of the inner loop. My question is how to decide the bandwidth. How we can decide the bandwidth of the controller? Before developing the controller, this is very important topic. You have to decide the bandwidth. See, once you know the bandwidth, it is easy to identify the KP and KA value. Clear? Our object of this program, GIAN program, is predictive control. If you want to control something, what it required, you should know actual system parameter. Now my question is how to decide the bandwidth. Any controller, whether it is a PA controller or hysteresis controller or model predictive controller, how we can decide the bandwidth of the controller? Your job is you have to focus on inner loop. Inner loop bandwidth you have to decide first. After deciding the bandwidth of the inner loop, it is not a big deal to decide the bandwidth of the outer loop. Clear? Now my question is how to decide the bandwidth. How to decide the frequency of the inner loop. How to decide the speed of the inner loop. Anyone? Electrical scholars? This is very important. These points you cannot find in any textbooks. How to decide the speed of the loop based on the system characteristics. You got my point? Example I will tell. You know about solar cell, PV cell? At least you heard about PV cell, even though you are not belongs to electrical or right. See electronics, even computer science people also, they can see, you know about PV cell or about, you know about LED light. LED light. What is the mathematical model for LED light? How we can represent LED light? Simple resistor. Electrical equivalent circuit diagram for LED is simple resistor, right? There is no inductance effect. Now, if take coil, take conductor, this conductor, what is the mathematical model or what is the electrical equivalent circuit for the coil? RL, R and L. Now tell me what is the difference between RL circuit and R circuit? Anyone? Okay, fine. Now current is lags, fine. Response also delay in RL circuit compared to R circuit. What is the problem with R? There is a problem is there with R. Sorry? Very good. See, the beauty of RL circuit is, right, it will not enter, current will not enter. Even if you apply voltage, current will accelerate. Even if you remove the voltage during certain period, current will not come zero immediately. Nothing but the ability of the RL circuit is, even if you eliminate the voltage across the terminal, current will not enter in discontinuous mode. But our problem is current will enter in discontinuous mode immediately. Reason is there is no energy storage element. You got my point? See, as a scholar, your job is, see what are the internal parameters of the system, you should know very clearly. What is the value of R, what is the value of L, you should know if inductance effect is more, you no need to go for high frequency. If student is very good, you no need to take more classes, you no need to take high frequency, you no need to operate with high frequency. But if student is below average, no option, you need to repeat the same topic more period. You have to increase the frequency. You have to operate the topic with more times. You have to teach same topic, same concept, you have to repeat 4 or 5 times. If students are very good, inductance effect is there, one single time is sufficient. They can extract this waveform. Problem with R is there is no energy storage element. Whenever you remove the voltage, immediately current is coming zero. Once your system is operating in discontinuous mode, issue is it will not obey your instructions. It will not, even if you're taking care about the control parameter in KP and KN PA controllers, or even if you're taking care about weighting factor in model predictive controller, problem will not solve. Clear? So this is the standard hierarchy. We don't have any option. You need to follow this hierarchy, even though it is a scalar control method or vector control method, right? You have to follow this structure. Then after that, later we'll adopt MPC method. Now come to model predictive control method. Under vector control method, this model predictive control will come under vector control. What is vector control? By adopting model predictive controller, we can able to control the magnitude and position instantaneously. You got my point? It is advanced control method. Now these all the methods are coming under, there are various control technique schemes are available for power converters, right? So one is hysteresis controller, right? Linear controller, sliding mode controller, predictive controller, artificial intelligence controller. See, out of this, see this method, model predictive control, become very popular compared to other methods. What is the reason? We can track the reference, we can improve the dynamic response, right? We can minimize the error. If error is minimizing, advantage is ripples are coming down. What is ripple? I will explain through MATLAB. You will get more clarity. Clear? So our focus is on, see, why we are moving to model predictive control is so important. What is the problem with PA controller? This slide will give clarity about what is the need of model predictive controller. This is about conventional PA controller. This is about model predictive controller. Now tell me here. Observe these two diagrams clearly. You will get more clarity about why model predictive controller is needed, why people are motivating towards model predictive controller. Example, you forget about this diagram, it is not clear. This is, I only drawn this diagram, it is not effectively. I will take simple example. Let us assume that at kth instant, what we are doing, we are calculating error. In PA controller, at particular sample, what we are doing, you need to know the information about error. This error, if you send through the controller, what you will get? Controller will give cost component. How much cost component you need to maintain in actual system, your controller will decide. That value you need to compare with high frequency triangle, that is called carrier waveform. If you compare the modulating waveform with carrier waveform, what you will get? You will get pulses. Pulses are duty period. Clear? You got my point? What is the output of the, what is the output? See, if you take sample, a particular instant, finally, after executing your logic, your logic will decide how much duty period, right? What is the duty period of the power converter will decided by the controller. You got my point? Nothing but your controller will decide the voltage, how much voltage we need to apply across the motor terminal will decided by the controller in conventional controllers. Take example PA controller. This is what we are doing. Am I correct or not? So in particular sample, we are calculating the error, we are generating the modulating waveform, we are in same sample, we are comparing the modulating waveform with carrier waveform, right? After comparing this comparison between the modulating and carrier, you will get pulse. If you apply this pulse to the power converter, your power converter will give the voltage. You got my point? This voltage we are not applying in the same instant. So your controller, your logic, whatever logic you are adopting in conventional controllers, that logic will give information about, see, how much voltage we need to apply in the next instant. You got my point? So in next instant, whatever voltage we are applying, that voltage is not completely responsible for rectify the error. In coming instant, what will happen? Error will change. Whatever voltage we are applying at k plus 1 instant, this is the instant. In this instant, we are deciding the voltage vector. What voltage we are applying in the next instant, we are deciding at kth sample. This voltage will applied across the actual system at k plus 1 instant. In k at k, at k plus 1 instant, voltage is V of k. This V of k is decided at what instant? Kth instant. You got my point? Now whatever voltage you are applying at k plus 1 instant, coming instant, that voltage is not completely responsible for rectifying the error at k plus 1 instant. You got my point? This is the problem with all conventional controllers, where see, whatever voltage is decided at kth instant, that voltage is applied in the, will apply in the next instant. See, in each sample, your control logic will decide the voltage value, duty period. That duty, based on the duty, what will happen? Your power electronic switches will regulate how much duty, right? It is a 40% or 80% duty, right? Will decided by the controller. If your switch is regulated with same duty, what will happen? RMS will change, average will change. These two are called effective values. By changing this effective value, we can control the variables. Now here, issue with conventional is, see, in particular sample at kth instant, we are calculating the error. We are calculating the error between reference and feedback signal. This error we are sending to the controller. Your controller is deciding voltage vector. You got my point? That voltage vector is the output of the kth instant. You got my point? That voltage is applied actually, practically that voltage, decided voltage vector will apply in the next instant. Whatever voltage is applied at particular instant k plus 1 instant, that is not responsible for E of k plus 1. E of k plus 1 is different. Whatever voltage is applied at k plus 1 instant, that voltage is responsible for previous sample error. You got my point? What is the delay between applied voltage and error? One sample delay. If your sample time is more, you will lose accuracy. If sample time is less, you no need to worry. But nowadays our systems are so complicated, our challenges, our requirements also more. Right? Based on requirement, what will happen? Challenges are also increasing. Number of constraints also increasing. Right? Burden on the processor also increasing. Then you have to increase the sample time. If sample time is more, definitely computation burden also more. This is a very big challenging, right, with conventional machines. Because of this problem, right, this problem will motivate to adopt model predictive control. In model predictive control, what we are doing is at kth instant we are calculating the error. What is the error? Right? Error. We are, see, in conventional method we are calculating the error. Whatever error you are calculating at kth instant, that error is E of k. But in predictive, what we are doing is, see, we are calculating the error at k, whatever error we are calculating at kth instant, that error is E of k plus 1. One sample before ahead, we are predicting the error. You got my point? You got my point? We are predicting the system behavior one sample ahead. If you know the behavior of the system, how systems are behaving in future state, if you know the information, it is not a big deal to calculate the error. Right? So then, at kth instant, what we are doing is we are calculating the error information about k plus 1 instant. So based on the k plus 1 error, your controller will produce the voltage vector that is called V of k plus 1. Clear? At kth instant, what we are doing is we are generating voltage vector which is responsible for next instant. So in next instant, definitely applied voltage is V of k plus 1. Whatever voltage vector is applied at k plus 1, that voltage vector is 100% responsible for rectifying the error at k plus 1 instant. You got my point? This is the delay. Because of one sample delay, right, this model predictive control, people are motivating towards model predictive control. In conventional, all hysteresis controller, PA controller, right, if you take any controller, conventional controllers, see, compared with model predictive controller, there is one sample, minimum one sample delay is there between, right, error and voltage vector. Whatever voltage vector you are applying, that is not responsible for rectifying the current state error. That voltage vector is responsible for previous state error. At current instant, error may regulate. Error will change. But in model predictive controller, what we are doing is we are predicting the error based on the actual system characteristics. Once you know the characteristics of the system, we can easily develop the equations. We can, based on the equations, based on the model, we can predict. We can predict the behavior of the system. How error is changing in the next instant, we can calculate. We can easily calculate at kth instant what is the behavior of the error in the next instant. We can calculate. Once you know the behavior of the error at kth instant, it is very easy to the controller to decide the voltage vector. Whatever voltage is decided at kth instant, that voltage is responsible for k plus 1 instant. Now our problem is solved. You got my point? What is the problem with conventional controllers? Whatever voltage we are applying at particular instant, that voltage is not responsible for current state error. That is responsible for previous state error. You got my point? But in model predictive method, whatever voltage vector we are deciding, that voltage vector will take 100% responsible for current state error. Because of this reason, if you observe this response, what is the difference between, you forget about what method we adopted, what is the difference between figure, this figure and this figure? Observe carefully. Is there any difference? Is there? Ripple, thickness. You got my point? See, this is about conventional hysteresis controller with PA combination. This is completely right model predictive controller. By adopting model predictive controller, what is happening? Ripples are coming down. What is ripple? What is meant by ripple? Ripple is nothing but difference between instantaneous and average value. If ripple, see, ripples are less, nothing but instantaneous and average values are closely to each other. This is the ripple. This is the average. If you take ripple here, this is the bandwidth of the ripple. Center point is the average value. Right? If ripples and average both are coming closely to each other, what is the advantage? Noise. In first case, noise is more. If there are any ripples are there in generated torque, this is the torque generated by the response with hysteresis controller. This is the nature of torque generated by the machine by adopting model predictive control method. Right? Now tell me, what is the advantage here? Ripples are less. Nothing but your instantaneous value is coming closely to average. If instantaneous value is coming to closely to average, noise is less. If noise is less, no oscillations in the speed response. If speed is not oscillating, passenger is more comfort in the electric vehicle application. You got my point? See, now how to develop this model. Now see, till now what we have done is we apply reverse engineering technique. Whatever technique I adopted, now till now we have not entered in the equation, we have not entered in the model predictive, but we identify the what is the need of model predictive controller, we identify what is the expected output of the model predictive we discuss, but we have not discussed what is the how to implement the model predictive controller. You got my point? So now come to our system. Our system is a motor. So this is a very important concept. See, whenever you want to, why model predictive control method becomes so popular nowadays is advantage is whatever system you want to control. See, advantage is we have mathematical model for all existing system. If you take drives application, I have mathematical model for DC machine. We have mathematical model for AC machines, right? So we have mathematical representation of physical system. This is the advantage. Once you're having mathematical model, we can easily predict. Now, what about this side? What about this side? This is about system characteristics. Clear? Now, what about this one? This is about converters. If you take, you know about inverter circuit, what is the function of inverter? It will convert DC to AC. If you take 3-phase 2-level voltage source inverter, there are 6 switches are there. There are 3 legs are there, right? This is the power circuit. Please try to understand. This is the power circuit about the inverter, power electronic circuit, inverter circuit. How many switches are there? There are 6 switches are there. Each switch having 2 states. So 2 power 3. So how many switching states are there finally? 8. Beyond that, nothing is there in your hand. By using these 8 switching states, we can able to control the energy transfer to the system. You got my point? Energy is, this is the source. This is the motor. Right? By changing the duty period of the switch, we can able to control the energy transfer from source to machine. Based on the customer required, based on the requirement, right? By changing the duty period, we can able to control. But see, whenever you want to implement model predictive controller, see, you should know system characteristics. What is the system? Motor. Right? Next, another important thing is to control the motor characteristics, what method, what product or what device we are adopting is so important. Here what device we are adopting? We are adopting inverter model, right? See, once you know the inverter characteristics and motor characteristics, it is not a big deal to develop the model predictive controller. This is the, please try to understand, this is the standard structure for model predictive controller. If you want to develop model predictive controller, you should know actual system model, right? To change the characteristics of the model, what device is required, you should know, right? How many switching states are there in the system, in the power electronic, with respect to power electronic model, how many switching states are there, you should know. What is the actual system model, you should know. By combining these two, we can easily develop the model predictive controller. You got my point? That's why next one more important thing is model predictive controller, it will not work for analog circuits. It will work only for digital circuit. In analog circuit, what is the issue? What is the problem with analog circuits? Yeah. Why? What is the reason? Predictive, fixed. Your clock frequency is fixed. You got my point? See, microprocessor, microcontroller, DSP, FPGA boards, all controllers, right? Clock frequency is fixed. It will not regulate. You got my point? So, if you take analog controller, we cannot implement predictive control method. Why? Because where this one's, what will happen? Sample switching frequency or execution time, all we cannot synchronize to each other. That is the issue with analog controller. But digital controller, once you know this clock frequency of the controller, right, based on the execution time, we can decide the sample time. Sample time, you have to take fix. You have to fix the sample time, right? Then see, for a particular sample, right? So what we are doing in model predictive controller, we are predicting the system behavior. We are predicting the torque and flux, how torque and flux are changing in the future sample. We are predicting, then we are calculating the error. 5 minutes. Fine. Yeah. See, if system is entering saturation, it is very difficult to bring back into linear zone, you know. So that's why I'm taking care about the saturation levels. I'm not bringing the system into saturation level. I'm always try to operate the system in linear zone only. Now already closely to 10 minutes to, right? I will try to wind up within 10 minutes. Okay. See here, what I'm trying to say is, whenever you want to implement model predictive controller, essential thing is you should know system behavior in terms of mathematics, right? Then after that, see what type of controller, what type of power electronic model we are adopting to change the dynamics of the actual system, you should know. Once you know the finite number of switching states, how many switching states are possible, what are the available switching states for existing converter, if you know, it is easy to implement, or it is very we can implement the combination of system characteristics and power electronic model characteristics. These two will give the, right, will work. See, if you know these two effectively, we can implement predictive control. Clear? Understood? So based on the switching characteristics, we can control the variables. But here, see, what is the problem with conventional controller? We discuss, right? Whatever voltage vector is decided at particular sample, that is not responsible for rectify the error at current state. That voltage vector is responsible for previous sample. You got my point? So that's why by using this mathematical model, by using the mathematical model of the actual system, we can predict the error. What is the nature of error in the next sample we are predicting, right? So based on the switching state, based on the finite number of switching state, we can identify the optimal voltage vector. You got my point? What we are doing in model predictive, we are iterating the cost function. What are the, see, many scholars, they are unable to identify the how to design the cost function. Whenever you want to design the cost function for a particular system, you should know target parameter. What are the target parameters for electrical drive? Our system is an electric drive. What are the target parameters? What are the target parameters? Torque and flux. These two things should be there in cost function. You got my point? These two you have to bring into cost function based on our system. Our system is a drive, motor. Whenever you want to control the motor speed or position, you need to control the torque. While controlling the torque, see, important thing is you need to minimize the number of variables in the torque profile. If you want to minimize the number of variables in the torque profile, you don't have any option. You need to maintain magnetizing flux constant. If magnetizing flux is constant, advantage is number of variables involved in the torque expression will coming down. We can convert it from nonlinear to linear. That's why these two variables you have to focus. No option. Same thing, same concept you can adopt to your system also. Whenever you want to adopt model predictive controller to your system, your job is you need to identify target variables. Right? What is the expected output of your system? You need to identify first. Right? To control that variable, what parameters we need to maintain constant, you should know clearly. Once you know the characteristics of the system, we can easily decide the cost function. This is the mathematical model for cost function in predictive controller for electrical drive system. Even if it is a induction motor, or even if it is a synchronous machine, or even if it is a BLDC motor, or even if it is a switch reluctance motor, cost function will not change. This is the fixed. Why it is fixed? In all motors, target variables are torque and flux. But if you want predict, here this is the reference torque. From where this signal will come? Reference torque, from where it will come? We discuss hierarchy, right? Reference torque is coming from speed controller. You got my point? Reference torque will decided by the speed controller. Second loop will decide the reference torque. You got my point? So here what we are doing, we are trying to focus on inner loop. If you focus on inner loop, automatically outer two loops will follow the inner loop. That is the strength of inner loop controller. That is what we discuss through this example, right? If you focus on inner loop, what is the advantage? Your outer loop will follow automatically inner loop. Clear? So that is, we are focusing on inner loop. If you focus on inner loop, we are trying to minimize the inner loop error. Automatically outer loop will follow the inner loop. Clear? Anyone having doubt up to here? This is the cost function. This cost function you have to iterate how many times? In a sample time, how many times you have to iterate this cost function? This cost function you have to iterate, right? How many times? How to decide the iteration, number of iterations? It is based on control circuit. It is based on power circuit. How many switches are there? See, here if you take this circuit, how many switching states are there? 8. Beyond that, nothing is there. With 8 voltage vectors, we need to iterate the cost function. Right? If you iterate the equation 8 times for different switching states, right? What will happen? Cost function value will regulate. At what switching state your cost function is coming down, that is called optimal cost function. Right? So, at the end of sample time, right, your cost function will decide the optimal voltage vector. That voltage vector is responsible for eliminating the error in future sample, coming sample. Why? Because here what we are doing, we are not calculating the error at kth instant. Please check here. See, what is the value of error here? K plus 1 error. We are calculating torque error at k plus 1 instant. Flux error at k plus 1 instant we are calculating. We are calculating next sample error. You got my point? So this is the advantage of model predictive control method compared to conventional methods. Even if you take hysteresis or PA controller or fuzzy logic, any method, there is a issue is there, one sample delay is there in error control. Error we are not control exactly at particular sample. Whatever error we are controlling on particular sample, whatever voltage we are applying at particular sample, that voltage is responsible for previous error. But by adopting model predictive control method, we can take care 100% responsibility to eliminate the error at same sample, right? Clear? So here, so based on power circuit, we can decide how many number of times we need to iterate the cost function. We can decide here 8 switching states are there with respect to power converters. You have to iterate with 8 times. So after iterating with available voltage vector, you will get different cost function, you will get different errors, magnitude will change. So if you take this one V2 will give optimal value of the cost function, where V2 is called optimal voltage vector. This voltage vector is responsible to eliminate the error in coming sample. You got my point? So this is how model predictive controller is working. If anyone having doubts, you can ask. Now because of time constraint, I need to stop here. I don't know how many participants are following or not. I don't know really. At least even if you understand delta X also, it is fine. Changing the system response delta X is also very important with input. You got my point? Clear? Anyone having doubt? So same, this is the response. This is the response simulation results, right? About the different methods. First one is PA controller with hysteresis base. Second one is model predictive control. You can see steady state error is very less. But conventional method, if you take, ripples are more. Clear? Shall I stop here? Okay, thank you. Sorry? Later, no. Later, later I don't have any session. Okay. If you have any doubts, you can post, you can request your coordinator. I will address. Okay. If you are having any query in future, you can write on paper, white paper. You can submit to coordinators. They will forward to me. I will respond through mail, or I will respond through any other technique. Okay. Thank you. I am telling. See, whenever you want to do something, first important thing is whenever you want to control system, right? Any method, first important thing is you should know actual system behavior. Through mathematics, you have to understand. If you are very strong in mathematics, almost 90% problem will solve. Okay? Thank you. See, because of time constraint, I'm not focusing on simulation also. No issue. Maximum inputs I have provided to everyone. Okay? Thank you.
Valuable insights in a slow and deliberative way.
So tomorrow we'll have the session from 10 sharp. Tomorrow the session would be on introduction to IoT. I think so I've shared for tomorrow. If not, I'll share it today. There was some changes which were happening, and I'll share the whole schedule today itself. So tomorrow we'll have introduction to IoT and case study in the morning, and afternoon we'll have a session there in the classroom there in electrical department. So when you go to electrical department, you actually, when you come to seminar hall, you take a right side, right? When you come from the Kalam hall, you take a right one. Instead, you take a left one. You will reach electrical department, exactly opposite to the seminar hall complex thing. Anyways, my scholars would be there, so they'll help you come up here. In the second half, we'll go with Arduino programming, introduction to that, and we'll try to make some programs in that. Probably you will be doing something into the thing. We'll also try to provide the Arduino boards to you so that you connect it and see it. Maybe only the initial part can be done in that, and then there are some other softwares that we can use. I assume that the internet is available to you right now. At least not, then tomorrow we'll have internet there. So you can download it from there. As such, internet is not required to a very large extent to download some big software, but to access some websites. That's it. So tomorrow we'll work into that. IoT introduction, case study, and Arduino programming. Yeah, thank you.